Now, why should you even watch this video? You can also easily just search up the laws of propositional logic online and then look at all the equalities. Well, in this video, I'm going to be talking about the things that aren't as obvious in the laws of propositional logic and some of the things that maybe you would miss in just the equality sheet online. So, stick with it. But anyways, let's talk about the first law. It's the double negation law. So if you have two knots, simply they canceled out and then you leave the previous statement. So if you get a statement A, all right, and you put two negations on it, the negations just cancel out, right? If you say I am handsome, right? I am not handsome, that's the same thing as just saying I am handsome, right? So if you have two negations inside of a statement, the negations just cancel out. This is called the double negation law. All right, how about the associative law? Well, let's write down A, B, V, C is equal to A, B, V, C. And if you don't know what this triple equal sign stands for, just think of it as equal sign, but for statements. Okay. But this right here is the associative law. Associative law. Now, here's the thing, an important thing about this. All these symbols need to be the same, and they can only apply for and or. Only the and or logical operators. So this right here is an example of the or logical operators here. Another example with and would be AB, wedge C, and A wedge B wedge C. This is the associative law. So you can kind of switch around the parentheses, but this is only if all the operators are the same between these, all right? If this right here was a and operator and this right here is an or operator, it will not work, all right? You have to use different laws for this. But if you have an or operator here and an or operator here, you can switch around the parentheses however you want. Matter of fact, you can just completely remove the parentheses altogether. You don't even need the parentheses, right? This right here would also be equal to A, V, B, V, C. This right here is also equivalent, and A, B, C is also equivalent to these previous statements. So this is the associative law. You don't even have to care about the parentheses, but keep in mind an important part of this condition and often mistake that people will make is they don't take into account that you need the same logical operators inside and outside the parenthesis. But on a side note, the reason why these laws are important is because they're important for when you're doing proofs. Ugh, I got some phlegm in my throat. And I'll actually do some proofs with the laws of propositional logic in the next video. I will leave the link down in the description when I actually post that video. But let's talk about the next law. Right? This right here is equivalent to B and A. Okay, so you can swap around the places. This is called the cumulative law. Right? You can just swap the places of two different statements if they have the same operator between them. Right? It doesn't really matter. The order in which you write this doesn't matter. This applies for the or operator as well. All right? You can swap B and A. And this also applies if you have more than two statements. So A, B, C. This is also equal to C, A, B. Okay? All these are the same cumulative law. There it is. And it's kind of similar to associative law in a sense, but these statements are still equivalent. Doesn't matter what order you write them. Keep in mind, you need the same operators between them. You cannot do this if you have an or operator here, okay? You can't do that, okay? If you have an or operator between the B and the C, you can't swap the places of the B and the C and the A anymore, all right? So keep in mind, same operators. These are very important for the cumulative law. All right, how about the idempotent law? And I highly suggest that you, actually I don't need to write it down. I highly suggest that you pull up like a sheet while you're watching this. But this right here is the idempotent law. All right, another example of the idempotent law is and A, and this is all just equal to A. All right, if you draw the truth table for this, it makes sense, okay? If you have the statement A and A, right, it just equals A, right? So let's draw the truth table for it. I don't know. You have A here, and you have true, false, okay? How about A, V, A, right? A with itself is just true and true, right? So we have a true here and a true here. So if you have true, true, take the or of that, still get true, right? If you have false, false, take the or of that, you get false, right? False or false is still false. So, and if you do the same thing with the other one, with the truth table, you'll get the same thing. So this is the idempotent law. If you have two of the same statements side by side with an or operator, or an and operator, they just all simplify to the singular statement. Idempotent. Here, I'll spell it for you guys. Idempotent law. Okay. All right. Next law, you have the identity law. I don't know why I need to spell that, but maybe for visual learners. But if you have an A and you OR it with a false statement, this simply becomes A. It's still A, right? So let's say you had A right here. Let's draw the truth table, and you had A or false. Okay. Well, if you have A, you just only get true and false, right? And if you compare A, every single combination of A with just false, you get true, false, right? If you OR this, it's still true, false. Still the same as A previously. So A v false is just equal to A, right? And also, A and T is still also equal to A. This is another version of the identity law. Here, I'll write down both of them. Right, so this is the identity law. Again, I highly suggest you draw the truth tables for these things. Helps a lot. And honestly, rather than memorizing them or just looking at the formula sheet every time, if you just know the logic behind them, you don't have to waste your time scrolling through the sheet to just, when you're in the middle of an exam, when you're on a time crunch, it helps a lot, right? Rather than just looking at the formula sheet constantly. But let's see. Next one is the domination law. Okay, so A v T or A or T. A or T is just simply equal to T, right? If you OR any output of A with T, then you will get still T, right? You will get true, right? True or anything else is still true. If there's one true in any OR statement, the output will always be true. And keep in mind, this A isn't only limited to one singular, all right? This A is not limited to a singular statement. This could be, I don't know, C or B here, okay? Or C and B. It could be anything. It could even be something larger, like, I don't know, a condition, and you have like 5 here. Okay, not 5. Fuck. A letter. Let's say variable. Next, what's the next letter? A, B, C, D, D, right? Okay. This right here could be the entire statement A, right? And if you have parentheses around here and you put an or around the true, no matter what the output of this statement inside the parentheses is, if you OR it with the true, it just simplifies down to a true, no matter what. Okay. So remember, these statements aren't limited to just one singular statement. They could be whole different sections. A could also be not P or something like that, right? But it's not limited to just a lone variable P or a lone statement, something else. It could be an entire section. That's one of the things that is a little confusing when looking at these equalities. Another domination law is A and false, right? If you have any instance of a false in any and statement, right, then no matter what A is, this entire thing is just false. This is the domination law. Completely dominates over anything, right? No matter what your statement A is, right, and it with anything false, true, false, whatever the output of A is, whatever, okay, it will always be false. So this is the domination laws. Next one, we have the complement laws. Let's write down complement. Complement is A or not A is equal to true. Okay, and you can actually write down the truth table for this. I can actually write it down relatively quickly. A, not A, you have true, false. Not A is false, true. And if we were to take the OR of both of these outputs, you have true right here, and you have false right over here, right? But there's always going to be true in this. So true or false, the output is true. How about false and true? So false for A and true for not A still has a true. So this OR statement will always be true. Therefore, any statement by itself, if you ORed the negation, will always output in true. And again, A is not limited. It is not limited to a single statement. You can have P and Q here or something like that, right? With V not P and Q. This also applies, right? You can kind of think of P and Q as a substitute for A here. So this would be A, V, not A, correct. And this is still the what's it called again? Complement law. There you go. And there's another version of the complement law, as expected. A and not A will always be false. And remember, if you do this, A and not A, right, there's always going to be one false. There's always going to be some false. If you not something, if it's a true value, okay, you know what? Why am I even trying to explain something without writing it down? All right, next law. It's the distributive law, kind of like the distributive property. But let's see, you have A and B, VC. This is equal to A wedge B, and the reason why I'm calling this a wedge is that's just how it works in latex, or law text. It's little computer software that allows you to write down math symbols on your computer. But this right here is the distributive law. Another version of the distributive law would be A, V, B wedge C, and A, V, B wedge A, C. Okay? And if you see what I'm doing here, we have A and then the AND operator, and we put the A and then the AND operator into the B. So we put it right in front of the B, and we put the A and the AND operator right in front of the C. And the thing separating it is your OR operator, right? So keep this in mind. I'm just taking the little front part and then distributing it into the parentheses. Okay? Now, keep in mind, one of the things that is not too obvious for this distributive law is that these guys need to be the flipped version of it. So let's see. You have an OR AND operator here. You must have an OR operator on the inside for the distributive law to work. And this goes the same for the other version. If you have an OR operator, you must have an AND operator on the inside of the parentheses that you want to distribute into. Okay. So let's look at the OR operation. A OR goes straight in front of the B. See that? We get A or B now. And A or C goes straight in front of the C, right? So you have A or here, and then A or also here. And then the operator separating them is simply the operator in the middle, right? And that goes right here, right? So if you see that little pattern, good for you. And now keep in mind, remember, A right here, or B or C, these aren't limited to singular statements. And you're likely going to get a problem on one of your exams or even on your homeworks where A, B, and C aren't singular statements. C could be, I don't know, P, V, Q, dash, I don't know, not Z or something like that, right? C could be this entire thing. But if you think of this entire guy as just the variable C, right, for your distributive, it'll help a lot for when you're applying distributive law. But keep in mind, these statements, A, B, and C, aren't limited to just singular statements. They could be entire sections, okay? But just think of these as variables that you can replace those big sections with. And you'll see what I mean when I do that, or when you guys watch that video on the proofs using propositional logic. But next one, De Morgan's law, very classic one. I covered this in a previous video, but I'll talk about it here because it's still a law of propositional logic. A, V, B is equal to, put 4 lines there. A, you flip the sign over, not B. So this is kind of like distributive law, but you're just distributing the negation in front of A and B. And remember, when you do this, you simply have to flip the AND or the OR operator. And keep in mind, this only works for AND and OR operators, all right? If you had a conditional, this would not work the same, okay? And another way you can use De Morgan's law is, again, the other direction, right? If you have an AND operator previously, the AND operator, once you distribute the negation operators, will flip to an OR operator after distributing. So keep that in mind. De Morgan's law, you must flip the operator in between the two variables. Now, how about absorption law? Now, this one's very helpful, actually. And unfortunately, I forgot about this one because it's at the bottom of the formula sheet. It's actually very, very helpful when you're doing proofs because it gets rid of a lot of distributive law, trust me. And distributive law is probably the one that's the most tedious. But right here is the absorption law. All it does is state that if you have two operators that are the opposites, okay, and you have A inside the parentheses as well as outside, it simplifies into A. Okay, and see how this is the AND operator, this is the OR operator. They are opposite operators, right? And we have an A in here and an A in here. Now keep in mind, the reason why this is different than distributive, okay, is because distributive, and let's write down absorption here so it's not confusing. Let's actually use different color. Absorption, right? And we have distributive here. Distributive looks like this, okay? B, V, C. And this is equal to whatever it is after, okay? So we have three separate statements here for distributive, all right? That is the key difference. Distributive has three separate statements. But absorption, so let's write down distributive here. Distributive has three separate statements, A, B, and C. But absorption only has two, A and B. And keep in mind, A has to be within the parentheses, okay, in order for all of this to simplify to A. Now, also, if you didn't notice that, what if you have B here, right? What if you have B here? Well, the thing about this is that the variables don't even matter. A or B doesn't even matter, okay, if you use A or B, as long as both the variables are on the inside. And the reason why is because we can just as well reorganize this. Let's actually erase the bottom. We can just as well reorganize this using cumulative law to just flip the place of the B and the A, okay? So we have B, not A. And this looks just like the same as the previous problem. Actually, this needs to stay as A, right? Because the output is A here. But this looks just the same, right? You just replace A with B, right? The variables are completely arbitrary. It doesn't even matter what order you place them, as long as you meet the condition for absorption, okay? That's the important part, right? All we did was replace A with B, and B with A, right? That's the only difference we did here. The variables don't matter. Keep that in mind. And remember to use cumulative law if you can to flip the place so you can get the absorption law more clear, okay? We have A, and this is the conditional identity. This is the last one. I promise this is the last one. This right here is just not A with or B. That is all. Okay. This is the conditional identity. If you have a statement A and you have a statement B, you just have not A or B. There's also another version of the conditional identity with the biconditional. You'll probably use this a little less. My class did not use it very much. But this becomes a dash B and B dash A. Okay? So this is the this is also conditional identity. Maybe call it the biconditional identity because it's a little different. But notice, if you want to do a proof, you can also apply the conditional identity onto these statements inside of here as well, after using the biconditional identity. So that's a little thing. And the last one, and I think this is the part of the complement law. Not certain, but basically, if you negate false, you get true. If you negate true, you get false. There you go, common sense, right? But that's really all for the video. If you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.